Okay, so today we are going to talk about multiplication of vectors. So by multiplication of vectors, how do we have multiplication of vectors? We have two methods in fact. So let me make a classification by saying that we have dot product, and this dot product is also called scalar product. And likewise, another one is cross product. Why we call it cross product is because we put a cross between the two vectors when we represent the cross product. And we can also just, if we have, for example, a vector A and then we have a vector B, then we can, and this is the angle between them, which is theta, represented by theta, and you can say theta AB, for example. So by putting dot between A and B is actually representing the dot product, and by putting the cross between A and B is actually representing the cross product. So it means that we have two types of vector multiplications. The first one is the dot product. So let's talk about the dot product first. Dot product, which is also called the scalar product, and product. So the dot products of product of two vectors A and B, it is denoted by A dot B, okay, and it is defined as the product of vector magnitudes. It is product of vector magnitudes. If A magnitude represents the magnitude of A and B magnitude represents the magnitude of B, so the product of vector magnitude and the cosine angle between the smallest, the cosine of the smallest angle between them. So cos theta AB. What do I mean by the smallest angle? The smallest angle between, in this case, A and B is this one. So, and there is another angle which is this theta, but we are not going to consider this angle. We are going to consider this smallest angle. So, so this is what the definition of the dot product is. So you take the magnitude of A, you take the magnitude of B, and then you take the cosine of the smallest angle between them. It also follows the commutative law. The commutative law is being followed by the dot product. It means that A dot B is actually equal to B dot A. Now, if I say that if I want to find out the projection of A, dot product give us another benefit. If you want to find out the projection of A on B, or in other words, you want to find out what A is in direction of B. So how can I find this out? So let me draw it again. If this is my A vector and this is my B vector, then if I want to have projection of A along B, so I will just project my A along B, and this is mathematical. So this is actually the projection of A along B, and it is mathematically what? If you multiply the vector with the unit vector of another vector on which you want to find the projection along, so this gives you actually the projection of A along B. And likewise, if you want to have projection of B along A, so then you multiply vector B with the unit vector of A. So we can also, so let me write it in this way. So what we can do is mathematically A dot AB, which is AB is the unit vector which is along B, and AA is a unit vector along A, and here is the AB in fact. So that can be actually written as the magnitude of A, obviously, as we defined over here, A, and then the second vector is AB, whose magnitude is obviously 1. So AB magnitude and then the cosine between theta A, B, obviously, because the theta remains the same. So this comes out to be A cosine theta AB, in fact. So what do I meant by this is that actually this is my A cosine of theta AB, where this portion actually represents the projection of A on B, in fact. So this part is my A cos theta B. Likewise, I can also have projection of B along A. So for that I need to dot the B vector with the unit vector of A in order to get the projection of B along A. So this is again B magnitude and then the magnitude of AA and then the cos theta AB, which gives us B cos theta AB. So this is another benefit of using the dot product, in fact. So let me take a figure and put it here. So this is going to make it more clear. Now look at this figure. Now this figure actually shows that if we had a vector A, if this is our vector A, for example, and this is our vector B, okay, now vector A is here and vector B is here, and this shows the unit vector of A and this shows the unit vector of B, and this shows the theta AB. Now if you want to project A along B, is like you project it here, and this is what we were getting from the previous formula, A cos theta AB. This is where it is. So this portion of the vector B is the projection of A along B. Likewise, if you want to project B along A, then that is B cos theta AB, in fact. So now I hope it is well understood. So this is what we are left with the dot products. Now let us formally go with furthermore with the dot product actually. So if I say A is, for example, since we are talking about, we till now have talked about only the rectangular coordinate system. So let us say I have a vector A which is AX in the direction of X, and then we have AY in the direction of Y, and then we have AZ multiplied with the unit vector AZ. And I have a vector B, let this be a cap head or bolded one. So this bold faced is actually my vector, and these are the component vectors. Obviously. This shows the component vector, this shows the component vector, in fact. So now here we have By in the direction of Y and Bz in the direction of Z. Now let us multiply them. Let we have two vectors and let us multiply them in this dot product fashion. So if you take the dot product of A and D, this actually can be written as AX plus AY plus AZ, and then a dot between them, and then AX plus AY plus BZ, and AZ. Okay, now this gives me, so this equals to this AX is going to go with the DX first, and then this AX is going to go with the BY. What I have written here is incorrect. This is BY, and then this AX has to go through the BZ. So likewise, AY has to go with the BX, and AY has to go with the BY, and AY has to go with the BZ, and so on. So let us do it. So AX, BX, and here comes the unit vector AX dot AX. Okay, since they are component scalars AX and BX, so they just simply multiply. For example, this has a value of 2 and this has a value of 1, so this gives you 2. And but the concept lies in multiplying the unit vector. So let's go further on, and this AX has to go with the BY, and the unit vector AX dot AY. And then we go with the AX goes with the BZ, and let me write it downwards, and then, okay, let's do it here, no problem. And then this is AX dot AZ. Okay, now again, AY has to go with the BX, so AY unit vector multiplied with the AY with AX. Likewise, AY will go with the BY, and here lies the same unit vectors AY and AY, and then AY is going to go with the BZ, so AY AZ. Likewise, AZ is going to go with the BX, and AZ AX plus AZ has to go with the BY, and AZ dot AY, and then it's getting a bit lengthy, but it's going to be reduced in a very good and nice form, and a presentable one. We are going to appreciate that. So this at the end goes with the AZ BZ, and AZ dotted with AZ in fact. Now if you look at the angle between the like unit vectors, so the like unit vectors have obviously a theta AB of equal to 0 degrees, and this implies that the dot product of them gives us 1. While the dot product, so it means that AX, for instance, we have AX and AX, this gives you 1. And we have AY and AY, this gives you 1. And we have likewise AZ and AZ, this gives you 1. So all the like vectors are going to give you 1 in fact. But all the other vectors, they are unlike, they are going to give you 0, because the theta AB between the unlike vectors is 90 degrees, because we know that if this is my AX and this is my AY, and if this is my AZ, then the degrees between them is 90, 90 and 90. So since that we have a cosine, so it gives us dot product equal to 0. So I can say that so I can have AX or into any unlike vector, this is going to give me 0, BX into AY give me 0, and so on. So all the unlike vectors are going to give me 0. So in this case, this goes 1, this goes 0. Okay, let me do it with another color. So this goes 0, this goes 0, this goes 0, because of the unlike vectors. This goes 0, this goes 0, and this goes 0 as well. What we are left with is this guy ax bx, and this guy and this guy. Simple as that. So it means that I'm going to get, at the end, I'm going to get a dot b is going to give me ax bx plus, because we get 1 over here, b sorry, ay by plus az bz. So this is the final result of dot product of a and b, where a has x, y, and z components and b has x, y, and z components. So this is how we found the dot product of two vectors. So we studied few things about the dot product. First is that it is a scalar product, and if you want to find out the projection, we can find out the projection, and you normally take the cosine of the smallest angle between the two vectors, and you just multiply the magnitude of those vectors. You multiply the magnitudes of, for example, if we have a and b, and you take the cosine of theta a and b. So this gives you the dot product, in fact. Now the second one is the cross product. The cross product is, we are going to start with the cross product. So the cross product is between the two vectors is a bit different than the dot product. It is denoted by a cross, that is why we call it a cross product, and it is defined as the product of vector magnitudes and the sign of the smallest angle between them with a vector direction defined by the right hand rule. So what do I mean by this is, again, we have the magnitudes of a and b, okay, and then we take the sign of the smallest angle between them, and also we have a unit vector that is normal to the, okay, let me try to write it in the textbook terms. So it is an, which is normal to both a and b. This is a very important concept, in fact. So let me draw it here. If I have, okay, let me draw this first. If I have a in this direction, and then I have b in this direction, and let this be theta a b, then this is the, then this is the normal vector an, which is normal to both a and b, in fact. Okay, so keep this in mind that this is the definition. Let me repeat that the cross product of two vectors a and b, for example, denoted by a cross b, is defined as the product of vector magnitudes and the sign of the smallest angle between them with a vector defined by the direction by the right hand rule. What do I mean by the right hand rule? So if a is in the direction of fingers, and then you rotate your fingers of right hand, so the thumb is going to direct in the direction of the normal unit vector. So it goes round, theta AB goes round, and then this thumb actually direct in the normal vector. Okay, so let's note few things about the normal vector. First thing is that the unit vector an is normal to the plane. So let me write the unit vector an is actually normal to the plane in which a and b lies. vector A and vector B law. Okay. And the second point to be noted is that AB sine theta AB is actually area of the parallelogram formed by the vectors A and B. Okay, yes, it makes sense. Of the parallelogram formed by vectors A and B, in fact. So now let's jump into the simple example by doing some simple example as the case we did previously. Let it be A and B. We are going to take the cross product for. So let A is actually again equal to AX plus AY and plus AZ in the direction of AZ. Likewise BX and BY and BZ and so on. So when we do the cross product of them, so again we are going to have this situation that we are going to have AX and then BX and the unit vectors AX cross AX. Okay, and then we go for AX and then BY. Okay, and here we have AX cross AY, and then we have, let me go further this way, and then we have AX, it goes with the BZ, and this gives me AX cross AZ, and then coming back, this gives me, now AY goes with the BX first and AY unit vector with the AX, and let me complete it all. So AY again goes with the BY, AY cross AY, and then AZ goes with the, AY goes with the BZ, which means that AY unit vector into AZ unit vector. And now AZ goes with the BX and AZ cross AX plus AZ BY and AZ unit vector cross with the AY. And likewise, we are left with the last term, and that is AZ. It goes with AZ goes with the BZ. In fact, so AZ cross AZ. Now this gives me. This put me in a situation that I need to now define so I need to define something about the cross products, in fact, of like unit vectors and the unlike unit vectors. Now the cross product of like unit vectors yields 0, because the theta AB between them is 0 degrees, and since we are taking the sine of the angle between them, so sine of the 0 gives us 0, and like unit vectors like unit vectors product, cross product is 0. But if it is unlike, then since the unlike vectors have angle between them 90 degrees, and this 90 degrees gives us a value of different unit vector. In fact, so how to find this out is, what we can do is we can simply say if this is ax and then this is ay and then this is az. So what you can do is you can go right side, right hand rule again. So ax crossed with ay is going to give you az, because as we discussed that any two vectors, when we cross them, it is going to give us so what you do is you take the magnitude of ax and magnitude of ay, and then you take the sine of the angle between them. So that is actually, and then the sine of angle between them is again 1, so you get ax. So let me write it: ax magnitude and then ay magnitude, and then you take the sine of 90, which is actually 1. So let me write it first: sine of theta ax ay and sine 90 is actually 1, and then you take the an, the normal unit vector actually. So this an over here in the case of ax and ay is actually what? If this is ax, sorry, this is ax and this is ay, and it gives you az in fact. So the cross product of ax and ay in this, with this concept, this goes 1, this goes 1, this goes 1, this goes az. So this is az. So let me guide you in a way that it is easy for you to remember. So whenever we are going to go in this direction, for example, ax into az is going to give you ay. Sorry, this is through. I had a mistake, so not this way, not this way. So let me do it. Since I told you that the direction or the resultant of the cross product of two unit vectors is going to be determined with the right hand rule. So what do I mean by this is ax into ay in the right direction is going to give you the third one, which is az. Az into ax is going to give you ay. Okay, and you go on. If you go in the right, in the opposite direction, if you say ay into ax, this is going to, against the direction, it is going to give you az, but it is going to be negative. So what I mean to say is, let me write all of them. Ax cross ax is equal to 0. Ax cross ay is going to be ax cross ay, so it is in the right direction, it gives you az. And ax cross az, let us look at here, ax cross az is going to give you ay, but with a negative sign. I hope it is clear. Let's go with another color. So now ay, when it goes with the ax, sorry, when it goes with the ax, so ay when it goes with the ax is actually going to give you ay. Let me look at here. So ay when it goes with the ax, so it is here and it is in the other direction, so it gives you minus az. Likewise, ay cross ay, since the sign 0 of 0 is 0, so it is going to give you 0, and ay when crossed with az is going to give you ax. Now see, ay when crossed with the az, it is going to give you ax. So the last one is the other one. It is let me take a yellow color, and then AZ when crossed with AX. So you have to look at the figure in order to figure it out with the right hand rule, and it gives you AY straight away. AZ when crossed with AX, it gives you AY. Likewise, AZ crossed with AY gives you minus AX, and again the like unit vectors are going to get 0 when they are crossed with one another. So in this way, we are left with a very nice result, in fact. So let me write the final result for you. So this, the resulting vector is A cross B is actually, when you simplify it according to all these, by just putting all these values you are getting from the cross product of the unit vectors, you are going to have AY. So I leave it for you. You just do it by yourself, and you are going to get this at the end when you solve it. AY BZ minus AZ BY in the direction of AX, and then AZ BX minus AX, X, and then BZ in the direction of AY, and then the last one is AX BY minus AY BX in the direction of AZ. And there is another nice way to make it in a compact form, and that is also easy to remember. So you can also simplify the whole equation, this whole equation in this way, by writing A cross B, and then you just take a determinant, and then you say AX, then you say AY, then you say AZ. You write them in the first row, okay, and then you go with writing AX, and then AY, and then AZ, and then you write BX and BY and BZ. When you solve it, you are going to get the same result. So this is rather easy to remember, and this is what the resultant of the whole cross product is. Actually, this is the cross product resultant. So you need to remember this one in order to solve the cross product between the two vectors, in fact. So we can also go for a simple example if you like, but the concept is going to be the concept is now very clear, that we studied two things. One was dot product, and another one was cross product. So the cross product is the one we studied just right now, and the dot product was A dot B, and this was A cross B. Okay. Further comparison of them is we take the cosine of the theta between the smallest angle between the two vectors, and here we take the sine of the smallest angle between them. We have a normal vector to the plane in which A and B lies. It is also the product, the end result. And here we have a straightforward cosine of that particular unit vector. And here we had the same unit vectors. The same unit vectors gave us 1, and the unlike unit vectors gave us 0. But here it was different. It was calculated through the right hand rule, AX, AY, and AX, AY, and AZ, and going right hand rule, right hand rule, right hand rule. So if you cross AY with AX with AY, it gives you AZ. If AZ goes with AX, it gives you AY, and so on. And the like unit vectors gave you 0. So this is all about the two cross products and the two vector multiplications, the cross product and the dot product, and we dealt with a vector that has ax, and then bx, and then it has ay, and az and az. So this was in rectangular coordinate system. We took the same kind of a vector and we multiplied them in both cases, and we found the resultant vectors of both of them. And in the case of cross product, this was very easy to remember, the cross product of A and B.